Welcome to this 10th lecture of compiler construction. This lecture is very important as we are going to implement predictive parser for a sample grammar here. Okay, so in today's lecture we will get some sample grammar. It will be a simpler grammar because the focus is to get the concept of implementation of predictive parser. For sake of simplicity, we will get some simpler grammar. As that grammar will be recursive, so we will remove left recursion from that grammar, and we already learned that how to remove left recursion from grammar in last lecture. Okay, and then we will get we will apply the first function on all non-terminals of the resultant grammar that we will get after removing left recursion from our original grammar. Okay, and after these all steps we will try to learn that how to write the code for predictive parser. I have chosen C++ language for this purpose for sake of simplicity, but you are free to choose any language. Okay, the main idea is to get the concept, or the main idea is to know about the algorithm for implementation of predictive parsing. Okay, and at the end of this lecture there is an assignment in order to get some practical about today's lecture. Okay, so we will try to implement predictive parser on this grammar, which is our traditional grammar which we are using since second or third lecture. This is the grammar of an expression, and according to this grammar there are only 4 possible operators, and all are left you can say of left associativity, and the lowest precedence operators are plus and minus, and after that the multiplication and division are of higher precedence. And for sake of simplicity I have not get the possibility of 10 digits, rather I have chosen only 2 digits. Okay, so the operands are 0 and 1, these 2 tokens, and operators are plus, minus, multiplication and division, 4 tokens. Okay, as operators. Okay, so this is our simpler grammar, and as this grammar has some left recursion, so first of all the task is to know that where the left recursion exists in this grammar. Okay, so in these first 2 productions as well as here in these 2 productions left recursion exists, and here we recall our general formula to remove left recursion from a grammar, and we learned this formula in last lecture. So the formula was, if some non-terminal is in such a form that there are 2 left recursive productions, and then after that there is some non-left recursive production in that non-terminals grammar, then you can remove the left recursion from this grammar in such a way that choose the right side of production which is not left recursive. Okay, means for example here a can have the form of a alpha or a beta or gamma, so you will choose of course gamma. Then the first production will be a can have the form of gamma and some new non-terminal, where this new non-terminal can have the form of whatever the remaining in first production after that non-terminal, means alpha, and then that new non-terminal will come, means b can have the form of alpha b, or b can have the form of beta b, or B can have the form of epsilon. Okay, so according to this formula, we can remove left recursion from this grammar as expression can have the form of expression plus digit, or expression minus digit, or expression can have the form of digit. It can be represented as expression can have the form of digit, a new non-terminal, let's say rest, or rest can have the form of plus digit rest, or rest can have the form of minus digit rest, or rest can have the form of epsilon. Okay, so according to this formula, we can remove left recursion from our grammar. For example, here we have used the first production as exp can have the form of term rest1, a new non-terminal, where this new non-terminal can have the form of plus term rest1, or minus term rest1, or this new non-terminal's emptiness means its epsilon production. Rest1 can have the form of epsilon. Okay, similarly the term can have the form of term rest2. Okay, I'm sorry, here the digit should come. Okay, the term can have the form of digit rest2, where rest2 can have the form of multiplication operator, then digit and rest2, and similarly rest2 can have the form of division operator, digit and rest2, and also rest2 can have the form of epsilon. Okay, where the digit can have the form of 0 1. Okay, so here make one correction. Here is a mistake. The term can have the form of digit, here not term, here digit rest2. Okay, the term can have the form of digit rest2, and rest2 can have the form of rest of the productions are okay. So there is one mistake here. The term can have the form of digit rest2. Okay, so look here, here it is corrected. The term can have the form of digit rest2. Okay, so after removing the left recursion from this grammar, here is the resultant grammar. And now we can make the predictive parser for this grammar. So in order to write code for such a predictive parser, the best practice is to apply first function on all non-terminals of this grammar, because the first function always return those tokens from which tokens that non-terminal can start. Okay, so it will help us to write conditions in the code that if your current token, or you can say your look ahead, is that token which is within the first set of that non-terminal, so it means then in that case that non-terminal's production can be used, otherwise it cannot be used. So that's why we try to apply a first function on all non-terminals of the grammar. So here exp is a non-terminal, rest1 is the non-terminal, term is the third non-terminal, rest2 is the non-terminal, and digit. So here 5 non-terminals. Okay, so first of exp, there is only one production of exp, and that is going to start from term. So it means first of exp is equal to first of term. Okay, so we cannot decide here because there is no directly starting token on the right side of the production. So whatever the non-terminal is, first of all we have to get the first of that non-terminal, then we will get the answer of first of exp. So it means first of exp is equal to first of term. And when we will see the terms productions, there is only one production here. Term can have the form of digit rest2, so it is going to start from the non-terminal digit. So it means the first of term will also be equal to first of digit. Okay, so we have to find the answer of first of digit, and because there are two productions of digit, then that's why the set resultant set will be 0 and 1. Okay, so for example, in here there are 10 productions. A digit can have the form of 0, a digit can have the form of 1, or and so on. Digit can have the form of 9. Then of course here 10 tokens will come. Okay, so that's so simple to understand. Okay, so you can directly get first set of digits from here, from this grammar, and then after that you can say that the same set is the first answer of term and the first answer of expression. Okay, so first of exp, first of term, and first of digit all are same, and that is the set containing two tokens 0 and 1. Okay, now we will see what is the first of rest 1. So here three productions are. First production is going to start from token plus, and second production is going to start from token minus, and third production is epsilon. So just recall the concept of first function where we had learned that if some non-terminal have such form, means it has epsilon production, then epsilon must also be the part of its first set. Okay, so it means in case of rest 1 as well as in case of rest 2, the epsilon will be the part of its first sets. And when we see rest 1, the first production is going to start from token plus and second production is going to start from token minus. So it means first of rest 1 has a set which contains following tokens plus, minus, and epsilon. And similarly rest 2's first production is going to start from multiplication token and second is going to start from division token. So these two tokens are within this first set of rest 2, as well as epsilon will also be the part of first function of rest 2. Okay, so we have found the first function sets for each of the non-terminal within this grammar. So now we will start coding for predictive parser for this grammar. Okay, now look here, the grammar is shown here as well as the first functions are shown here. As you know that predictive parser is a specialized type of recursive descent parser, and we already had learned that in recursive descent parser there is a function for each non-terminal of the grammar. Okay, so first of all we will try to write code for each of those functions. Okay, so the first non-terminal which we look here is exp, or you can say this that the start symbol of this grammar is exp. So we can write the function exp in this way. How we can write that? Because here is only one production of exp. Exp can have the form of term rest 1, means the right side of production has two non-terminals. First one is term and the second non-terminal is rest 1. Okay, so in recursive descent parsing approach, for each non-terminal there is a function. So it means whenever you come across a non-terminal, there is always a function call for that non-terminal. Okay, and you can see here there is no epsilon production for exp. So it means if we fail to implement this production of exp, then there is no other production of exp, or there is no possibility that exp can be empty. So it means that there is only one chance, and that is to either to implement this production or to report syntax error. So it means we are going to write this code by looking two factors or two things. First one is the productions of that non-terminal, and for your convenience I already highlighted that production that belonged to exp, as well as I have highlighted the first of exp's answer. Okay, the first of exp is a set containing 0 and 1. So it means the expression can only start from 0 or 1. So by seeing these two things, we can write the code of exp as, if the current token which you are going to see within the string of input tokens, if that current token and for as I already told you that the current token which we are going to see is called look ahead. Okay, so if the current input token means look ahead is equal to 0 or look ahead is equal to 1, then there is a possibility that it can be expression. Okay, so in that case we are going to implement the exp's production. And how we are going to implement? Because the first thing in this in the right side of the production is term, which is a non-terminal, so we are going to simply call the terms function. Okay, and after that the another non-terminal rest1, so we are going to call this rest1. Okay, so if look ahead is equal to 0 or 1, then we are going to implement this production. So it means the successful creation of parse tree will go on, otherwise the syntax error will be reported, and it will be confirmed that the sequence of tokens or the input tokens for which we are going to do this parsing, that sequence is not belonging to this grammar. Okay, and we have to report the syntax error for it. Okay, so I repeat, to implement or you can say to write the code for exp, we have seen two things: the productions of exp as well as the first function's answer for exp. So first function is saying that exp can start from 0 or 1. So if we have accordingly we have written this code, if look ahead is equal to 0 or look ahead is equal to 1, then we are going to implement this production, and then the implementation is very simple. If there is a non-terminal, then you just call the function for that non-terminal, and if there is a terminal, or you can say there is a token, then you are going to call a special function called match by giving that token as an input to that function. Okay, so you will see that example as well in next slides. Okay, so we have constructed the code for exp, and similarly we can construct the code for rest of the non-terminals. For example, the second non-terminal is rest1. It has two productions. First one is starting from plus, and second one plus token, and second one is starting from minus token, and the third production is epsilon. So epsilon means if we cannot implement the first production as well as cannot implement the second production, then there is no need to report syntax error. It just say the failure of you can say the in implementation of these two productions is just showing that rest1 is empty. Okay, so empty means you will do nothing, and just the control will go from this function. Okay, so according to this strategy, we are going to implement this function in a way that first of all we will see that whether we can implement the first production or not. The first production is going to start from plus token, so we are going to check that whether look ahead means the current input token is equal to plus. If that is plus, then it means the we have to implement this production. Okay, and for sake of implementing this production, we see the right side of the production, and on the right side the first thing is plus, which is a token. Okay, so in case of token, we call match function by giving that token which the grammar is saying. The grammar is saying here plus should come. Okay, by giving that token as input. Okay, so we are going to call match function by giving plus token as an input. Okay, and then term non-terminal. So the term non-terminals corresponding function call here, and rest one's function call here. Okay, so these three things, because these three things belongs to the right side of this production, so these three things are within the block of when lookadd is equal to plus. Okay, so if lookadd is not equal to plus, then it is going to check that whether lookadd is equal to minus. If that's the case, then it means it is going to implement the second production of rest 1, and the second production is going to start from minus token. So it means the first call should be of match function by giving an input this minus character. Okay, so then the term function, then the rest 1 function. Okay, and after that you have seen there is no else here, because we do not want to do anything if we are going to fail within this if as well as within this if. So we are not going to do anything, so we are just letting the control go away from this function. Okay, so letting the control go away from this function means we are considering rest 1 as an epsilon. Okay, similarly the next non-terminal is term. Here only one production of term is, and there is no epsilon production. So it means if we are going to if we will go if we will fail in implementing this production, then in that case we must have to report syntax error. Okay, the second thing we are going to see from first function, and it is saying that a term must start from 0 or 1. So accordingly its code will be if lookadd is equal to 0 or lookadd is equal to 1. So in that case we will apply this production, and this production saying that first the digit non-terminal and then rest 2 non-terminal. So the first digit call and then rest 2 call. So if we are going this if is failed, then syntax error must be reported. So here is another function error which we will see at the end. Okay, so there must be some function error here within this code of predictive parser, so that we can call that function wherever we think that it's appropriate to report syntax error. Okay, and similarly as we have seen earlier, the code for rest 1, similarly the code for rest 2 is, and this code is showing that if first of all we will see that first of rest 2 has three things. Okay, it can start from static or it can start from slash, means division, or it also has epsilon, which is showing that rest 2 has the epsilon production. So it's just kind of a reminder to you that while writing code for this function, you should not write report syntax error. Okay, so first of all you should try to implement this first production that is going to start from this static, and in that production's implementation's failure, you will start from try to implement the second production, which is going to start from this division operator. And in a worst case, when you cannot implement the first production as well as you cannot implement the second production, then you will do nothing, means you will not report syntax error, because rest 2 can have the form of epsilon. Okay, so if lookadd is equal to static, then this token against this token match static, then I'm sorry, here is here should the digit function should come here. Here is a I think you can say there is a fault. So digit function should come here, digit functions call, then rest 2 function call. Okay, and in else, if lookahead is equal to this operator, then match this token, then digit function call, and then rest 2 functions call. Okay, rest 2 functions call. Okay, Similarly, for digit there are only two productions and there is no epsilon production for digit. So it means if lookahead is equal to 0, just for this 0 token you will call match function by passing this token as an input to that match function. Okay, and else if lookahead is equal to 1, then match 1, else you will report syntax error. Okay, so that's so simple. And finally we will see, because we have already seen the code for all non-terminals, now we will see the code for match function. Okay, so match function is a function which gets as an input some token, and it is going to match that token with the lookahead. Okay, I repeat that in our case we are going to we are considering that the input string of tokens is in the form of a one-dimensional array of characters, or you can say in the form of a string. Okay, whereas in that string each character is going to show a token. Okay, so we are, for sake of simplicity, we are going to represent each token by a character. Okay, so that's why here the type of token is character shown here. Okay, and also you will see in the next slide that this input is our one-dimensional array of characters. So we have already declared it as a one-dimensional array of characters. Okay, so we will this match function will try to match the input token, which is in fact the currently lookahead, with this input token, with this token that is given by the grammar. Okay, so if lookahead is equal to the token t, which is in fact the input of this function, okay, then if in that case, in successful matching case, the lookahead will go to the next token. Okay, or in case that both tokens do not matching, then we will report syntax error. Okay, the reason is, whenever, for example, here whenever the match function was called, then a token is given as an input to this function. Okay, so why we have given this token? Because digit can have the form of 0 is saying that according to grammar the 0 token should come here. Okay, so according to grammar the 0 token should come here. Okay, so that's why the 0 token is going to be given as an input to this match function. And after that, when this inputs when this grammar suggested token comes here as an input, so we have the input string of tokens and the current token which we already seeing, that is lookahead. So we are going to match that lookahead with the recommendation of the grammar. If the grammar and our input are going to be successfully matched, then it means all is okay, and we have to go towards the next token. Okay, so in that case lookahead is equal to the next token in the input one-dimensional array of characters, or you can say the next token, you can say the next character in the input string. Okay, so the error function is very simple. Whenever it is called, it reports that there is syntax error, because it's the parsing stage, or you can say the syntax analysis stage. So that's why the error here is always the syntax error. So this whenever this function is called within the predictive parser, so it always say that syntax error is reported, and the creation of parse tree cannot be continued. Okay, so in that case we must have to exit from the program. So we are going to implement this command to exit from the program. Okay, so here is the structure of the main function, because I have chosen the C++ to show you the implementation of predictive parser. And you know that in C++ the control always starts from the main function. So in main function, first of all, a message is going to be displayed for user that enter string of tokens. So in our case, our assumption is that the string of token is going to be given as a sequence of characters. So that's why we are going to get the input of that string, which is in fact a one-dimensional array of characters. So first of all, we will set the look ahead, and that is set it as the first character of that string. Okay, so input of I, where I is a global variable. Okay, so in next slide I will show you that how the I will be declared. Of course, that is not declared within some specific function, because we are going to use this I within multiple functions. So that's why the best approach is to use look to declare look ahead, I, and input, all three things as a global variable. Okay, and whenever I will show you the I will be declared. The I is always declared or is always initialized, means declared as well as it is given the initial value of 0. Okay, so since I already have the value of 0, so it means when first time we will use this command means look ahead is equal to input of 0, then it means the first character of the input is given to look ahead. Okay, and after that the expression function is called. Why the expression function is called? Because exp is the start symbol of grammar. Okay, so we are using predictive parsing approach, and in predictive parsing approach the tree is always made from root node. Okay, so we are going to call the root node. Okay, if the control successfully returns here, then it means the tree is successfully passed, or you can say the given input string of tokens is successfully passed. So in that case we are just going to show that specific message of successfully passing, and we will just go out of this normal function. Means this main function will be terminated as a normal termination. Okay, but in case, as you have seen earlier, that in case the error function is called, then always it's not possible that control comes here. Rather control exits from somewhere else during the program execution. Okay, so in that case the syntax error will be reported and program will be executed. But in case there is no error while this parsing process, then the successfully control comes here, and this after displaying this message there will be normal termination of this program. Okay, so I hope you got the idea of how to write the overall code for this predictive parser, but I will give you a sketch for that thing as well. So here is the sketch of full program if you want to implement it. Because I have used the C++ language, of course, first of all you have to include some header files, and after that we are going to declare these three global variables. Okay, input, and as you see here I have given the size of 20, but because I am assuming that I will not give the input that must that exceeds with this limit. Okay, so if you have planned to give the bigger expressions as an input, so you can choose its length accordingly. Okay, maximum length, or you can say you can choose its size accordingly. Okay, so this is one dimensional array of character. You can say we are going to declare a string here in the form of one dimensional array of characters, and that is input. So and after that we are going to traverse this one dimensional array with the help of this variable I, and we are going to start it from 0, because we want to access first of all we are going to access input of 0, means the first character of this input. Okay, so after that we are also declared this look ahead function, look ahead variable. So these three variables, input, one dimensional array of characters input, I variable as an integer, and look ahead, which in fact represents the current token. And as we are assuming that each character is a token, so look ahead's type is character. Okay, so by declaring these three variables as a global variable, we can use these variables anywhere in the program. Okay, after that the best practice is to use the prototypes of all functions. By using this strategy, you can call any function from anywhere. Okay, and after that you will write the code which I already explained you and shown you. So it means, so you can write the full program that is going to implement a predictive parser. Okay, so at the end of this lecture I want that you should have a practice for this implementation. So that's why I recommend you to solve this assignment, which contains two parts. First part is to write complete program for this predictive parser of the same grammar which I already explained you, or you can say I have already given you the code. You just have to write this code and just implement it. Okay, and the second part is you have to execute these two examples of input string of tokens on your written program and check its output. Okay, and finally you have to print out the program as well as the screenshots of your demo runs for these two examples, and you have to submit this assignment on your allocated repository on Google Drive. Okay, so that's it. Thank you.